Well, how you doing today? My name is Bill Campbell, and we're going to be covering reading number 7 in quantitative methods, statistical concepts, and market returns. It sounds like an exciting study session, doesn't it? So let's go with this. We have a number of terminology, words and phrases that we have to cover. You have to understand these. They could ask you about these on the exam. Two different kinds of statistics. Descriptive statistics, which describe the properties of a large data set. So for example, I like to use the example of giraffes, capturing maybe 500 giraffes and computing statistics on those. Now obviously every giraffe has a height and a weight and a number of spots, and whether it's male or female, and on and on and on. We don't want to write down all of those statistics for each giraffe, so we may summarize those. We may, for example, calculate the average height of our 500 giraffes, or the average weight, or the range of heights, or the average number of spots, things like that. Those are descriptive statistics. Inferential statistics, that's where we take the descriptive statistics that we got from our sample of 500 giraffes and try to use those numbers to get an idea of what the statistics are for all the giraffes in the world. Now obviously we can't capture all the giraffes in the world. We only have our 500, but if it's a reasonably good sample, we can say a lot of useful things about all those other giraffes that we couldn't catch, because giraffes, frankly, are very crafty. So that's the idea of inferential statistics. We'll talk a lot more about that later. You need to know the difference between a population, all the giraffes in the world, and a sample, the 500 giraffes that we were able to capture. We'll talk more about populations and samples as we go along. We have 4 different measurement scales, and notice up at the top we have a mnemonic, noal. That's how they say it in French, noal. It's a mnemonic for nominal, ordinal, interval, ratio. A nominal scale, well, the word nominal, if you look up the word nominal in the dictionary, you will find it means in name only. It's exactly what it says. These are simply names for categories. The example we have here, robin, parrot, seagull, these are obviously different kinds of birds. If we have numbers or data under the robin category, we simply know that it's different from data that are under the parrot category or data under the seagull category. That's all we can say. They're different. We don't know anything about whether robins are bigger than parrots, smaller than parrots. All we know in a nominal scale, the different labels simply mean different kinds of data. An ordinal scale, now we have a rank. We assign numbers, 1, 2, 3, 4, 5. But it's only the order of the numbers that matters. The example that we have here is large cap, mid cap, small cap stocks, let's say. We know that a large cap stock is bigger than a mid cap stock is bigger than a small cap, but there's nothing about the scale that tells us how much bigger is bigger. All we know, if we numbered these from 1 to 10, all we know is that 10 is bigger than 9, 9 is bigger than 8, but there's no concept in an ordinal scale of 8 is twice as big as 4. That idea doesn't exist. It's simply 4 is bigger than 3, 3 bigger than 2, and so on. In an interval scale, now we add a little bit more subtlety to this. In an interval scale, the difference between the numbers really matters, and it makes sense. The common example for an interval scale is temperature scales. We give you Fahrenheit here. 40 degrees Fahrenheit is 10 degrees more than 30 degrees Fahrenheit. Similarly, 80 degrees Fahrenheit is that same 10 degrees more than 70 degrees Fahrenheit. We could do the same with the centigrade scale. 20 degrees centigrade is 10 degrees more than 10 degrees centigrade. 40 degrees centigrade is 10 degrees more than 30 degrees centigrade. The thing to remember about an interval scale is that it does not necessarily have an absolute zero. Normally when we think of zero, we think that zero means having nothing. Obviously, on the Fahrenheit scale, a temperature of 0 doesn't mean you have no temperature. Similarly, on the centigrade or Celsius scale, having a temperature of 0 does not mean you have no temperature. This is obvious when you realize that 0 degrees centigrade is not the same as 0 degrees Fahrenheit. So the 0 doesn't mean 0. It's simply a number on the scale. If we want that 0 to mean you have nothing, then we move to what's called the ratio scale. The ratio scale is similar to the interval in that the distances between the numbers matters. 200 is bigger than 100 by the same amount that 100 is bigger than 0. So it is an interval scale, but it also has the idea of having an absolute 0. When we say 0 on the dollar scale, we mean you have no money. Probably a common situation for some of you who are studying for the exam, right? You're poor students, you haven't saved up any money, you're waiting until you pass your CFA exam and you can start earning the big bucks. Until now, you're poor, we understand that. Make sure you know the difference between the different kinds of scales and you understand the characteristics. A possible way they could ask a question about this on the exam would be that they would give you the characteristics of a scale. They would tell you that the difference between the numbers matters, but there's no absolute 0. Would that be an ordinal scale, an interval scale, or a ratio scale? You obviously would know that would be an interval scale. That's what they need you to know. Some more terms for you to understand. A parameter, that describes the characteristic of a population. Could be the mean, could be the variance, could be the range, things like that. So for our giraffes, a parameter would be the average height of all the giraffes in the world. Average weight of all the giraffes in the world, the height of the tallest giraffe in the world, the weight of the smallest baby giraffe in the world, things like that. Those would be parameters for the population. A similar idea for a sample would be a sample statistic. So from the 500 giraffes we were able to capture, we might be able to calculate, for example, the average height of all of those giraffes. That would be a sample statistic. The reason that we calculate sample statistics is that we want to use those to try to infer, try to come to some conclusions about the parameters for the population. We can't observe the parameters for the population because we can't capture all the giraffes in the world. Remember, giraffes are crafty. So we capture 500 giraffes. We hope, if we're lucky, that we will have an unbiased, good sample of all the giraffes in the world. We calculate statistics for them. We use those to infer statistics about the whole population. A way that we can summarize these data is the next bullet point, what we call a frequency distribution. This summarizes large data sets by assigning them to intervals. So for the heights of our giraffes, for example, let's say we were measuring the heights in meters. We might take our 500 giraffes and figure out how many of them are, I don't know what the smallest giraffe is in the world, probably not less than a meter tall. So let's say the smallest giraffe in the world is 1.5 meters tall. So we would have maybe a interval of 1.5 to 2 meters. How many of our 500 giraffes, their height falls into that? Then 2 to 2.5 meters. How many giraffes fall into that interval? 2.5 to 3 meters. How many fall into that interval? And so on. That's a frequency distribution. That helps summarize the data. Instead of having 500 data points, now we might have 8 or 10 intervals, and we have the number there. Makes it a little bit easier to handle. The frequency distribution can be either absolute numbers, as I was just describing. Of our 500 giraffes, maybe 50 of them are between 1.5 and 2 meters tall, and 120 of them are between 2 and 2.5 meters tall. and 180 are between 2.5 and 3 meters tall. That would be an absolute frequency distribution. Or we could do a relative frequency distribution. What percentage of our giraffes fall into each one of these intervals? 10% of them are between 1.5 and 2 meters tall. 15% are between 2 and 2.5 meters tall, and so on. That's a relative frequency distribution. If we were to draw a picture of this, a relative frequency distribution might give us a graph that looks like this. You're going to have to forgive me, I'm a horrible artist here. But that would be a relative frequency distribution. Very few giraffes down here that are extremely short, very few giraffes that are extremely tall, lots of giraffes in the middle, lots of giraffes in the 2 to 2.5 to 3 meter range. I'm not sure how tall the tallest giraffe is, maybe 4 meters. So maybe this is about like 2.5 to 3 to 4 meters, this range in here. So this here would be our relative frequency. Now the cumulative frequency, instead of putting the heights of the giraffes into bins, what we do is we calculate how many giraffes have a height less than a particular number. So we don't divide them up into bins where we have heights between, let's say, 2.5 and 3 meters, but we would look at all the giraffes whose height is less than 3 meters. So that would include all the ones between 2.5 and 3, and all the ones between 2 and 2.5, and all the ones between 1.5 and 2. It's cumulative. We start from whatever the smallest number is, and we add them all up to our boundary. So if you think about the graph of this, down at the very bottom, let's say our bottom number is 1.5 meters. Well, the smallest giraffe we decided was 1.5 meters tall. There are none that are below that. So we'll have a 0 down there for the number of giraffes whose height is less than 1.5 meters. Once we get up to a height of, say, 4 or 5 meters, well, there aren't any giraffes any taller than that. So 100% of the giraffes would have heights less than that. We're simply adding up all the heights as we go along, or the number of giraffes at each height as we go along. The graph for this would start down here at 0, goes along, then it starts increasing as we have more and more giraffes less than this height, and then it peaks up somewhere here. That's supposed to be horizontal up there at the top. This then is a cumulative frequency distribution. Statisticians sometimes refer to this curve as an S curve. You can see it's sort of shaped like the letter S, so they refer to that as an S curve. On the next slide, we find that these graphics guys are a lot better at drawing pictures than I am. This is a histogram. A histogram shows the relative frequency. Now here we have the relative frequency in absolute numbers. The data here are annual returns for a number of companies. So we have one company whose return last year was somewhere between -30 and -20%. This company was doing really lousy. They lost somewhere between 20 and 30% of their stock value last year. Between -20 and -10, well, we had two companies whose stock value lost somewhere between 10 and 20% last year. -10 to 0, we have three companies. So three companies lost between 10% and 0% last year. Finally, we get over here to the middle. Finally, we have some companies that actually had their stock go up in price last year. 7 of them, to be exact, had the return on their stock between 0 and 10%. 3 companies had the return on their stock between 10 and 20%, 2 between 20 and 30, and 1 each between 30 and 40, and 40 and 50. This is called a histogram. We fill in these rectangles, makes it very easy to read these data. We could have written these data down in a table. We could have had a column on the left with the range -30 to -20% in the first row, -20 to -10% in the second row, and so on. And then in the right column, we would have one company in the first, and two companies in the second, and three companies in the third. A lot of people have a difficult time reading tables like that and really getting a feel for the data. When you do it graphically like this, you create a histogram. It makes it much easier to see that we have this big peak here, that it does tend to slope off very similarly in both directions. A lot of people find that a lot easier to visualize, a lot easier to understand what the data are telling them. A histogram is one way of presenting these data. A similar, related way is what we call a frequency polygon. It's the same data that we had in the histogram, but now instead of having solid filled-in rectangles, we simply have a data point at the end of each interval. So we would have a data point here at -20%, and a data point at -10%, and a data point at 0%. And then we connect those points with this line. So this frequency polygon is presenting exactly the same data that we saw on the previous slide in the histogram, but it's presenting it as a polygon. Slightly different presentation, same data. You have to know which one is which. They could ask you a question. They may describe the kind of graph and ask you to tell whether it's a frequency polygon or a histogram or something else. That's the sort of thing you need to know about this. All right, finally we get to do the calculations. You're rubbing your hands and you're saying, oh good, we finally get to do some calculations. The first calculations we're going to do are on what we call measures of central tendency. This is within our data set. These are numbers that are somewhere in the middle, hence central tendency. We hope that our data tend to cluster around these numbers. So we calculate a number in the middle. Our data are somewhere around these numbers. We expect probably we will have more data points around these numbers, and then as we get further and further from these numbers, our data will get sparser and sparser. The calculations for arithmetic mean, which is the most common measure of central tendency, calculations are very simple. There's probably not a person in this class who hasn't seen this calculation sometime in the past. The sigma, this is a Greek capital letter sigma. That sigma notation says we're going to add up all these numbers. The x sub I, that is the ith data point that we have. For our giraffes, notice this says population, so we're talking about all the giraffes in the world. Each one of these x's might be the height of that giraffe in meters or in centimeters or in inches or whatever unit you're using for measuring the heights of giraffes. So we take the height of the first giraffe, add the height of the second giraffe, add the height of the third giraffe, and so on. That's what this notation means. The sigma, that's a Greek sigma. Sigma is supposed to conjure up the idea of sum, S for sigma, S for sum. So we take the sum from starting with 1 going up to n. Capital N is the number of giraffes, all the giraffes in the entire world. Add those numbers. So you get x1 plus x2 plus x3 all the way up to x, I don't know how many giraffes there are in the world, 50,872. Add them all up, divide by n. That gives you your average. Notice that when we are talking about a population, the value for this parameter, we always use a Greek letter. This will be consistent throughout the curriculum. When we're talking about a population parameter, we use a Greek letter to designate that. Because we have x's here for our values, we decided to call each one of the heights of our giraffes an x. We might write this mean as mu sub x. That's a Greek letter mu, lowercase Greek letter mu. So you might want to put a little sub x down here. If I can draw this, how good am I at drawing this? There we are. If you can read that, that's a mu sub x, to let us know that this is coming from measurements that we were calling x's. That's the population mean. The sample mean, now we go to our sample of 500 giraffes. We do the same thing to calculate the sample mean. We use a little n to designate this is how big our sample is. I think the idea is that there are a lot more giraffes in the world than there are just the 500 in our sample, so we use a big N to mean all the giraffes in the world. We use a little n to mean only the 500 in our sample. We add up the numbers, height of the first giraffe, height of the second giraffe, all the way up to the height of the 500th giraffe, divide by 500. That gives us the sample mean. For a sample, notice we use English letters to designate the statistic. So whereas we used mu, a Greek letter, for the population, we use X for the sample. And we put this little line over the top. That's called a bar, and the way you read this term is X bar. So X bar means the sample mean. Very easy calculation. Have to be able to do that on the exam. They will give you some data. You are going to have to calculate either a population mean or a sample mean on your exam. Here's another kind of a mean. It's the geometric mean. Now, properly, for general data, if we were talking about the heights of giraffes, let's say, the geometric mean, instead of adding up all the heights of the giraffes and dividing by n, we would multiply the heights of all of the giraffes and then take the nth root. That's a geometric mean. Now, the specific application to finance is just a little bit different. And I want you to come down here and take a look. I'm going to box this thing off. I want you to take a look at this formula down here for the periodic compound rate of return. Notice what people in finance do. Whenever they talk about rates of return, interest rates, growth rates, yields, whenever they talk about rates of return, before they use that number, they always add 1 to it. So that the number that you get, 1 plus this rate of return, that's the factor by which you will multiply your beginning value to get your ending value. So when we do the geometric mean, instead of multiplying just R1 times R2 times R3 up to Rn and taking the nth root, first we add 1 to each term. 1 plus R1 times 1 plus R2 times 1 plus R3 and so on, all the way up to 1 plus Rn. Take the nth root of that. Now below this, I would like you to write down what I think is a better way to remember this. I'll come down here and I'll get you some text here. And I want you to write down 1 plus R compound, the compound return, and I can't do a superscript here, so I'm going to use the little caret mark. 1 plus the R compound to the nth power equals 1 plus R1 times 1 plus R2 all the way up to 1 plus Rn. Algebraically, the formula that I just typed in is exactly the same as the one that you have above it. The periodic return is 1 plus R1 times 1 plus R2, 1 plus Rn, multiply those all together, you take the nth root and you subtract 1. The thing I like about writing it the way that I showed you is that now we have 1 plus R everywhere in this formula. We have 1 plus the compound return over there on the left. We have 1 plus each of the individual returns over there on the right. We have n factors on the left. We have 1 plus R compound times 1 plus R compound times 1 plus R compound multiplied, n of those multiplied together. On the right, we have 1 plus R1, 1 plus R2, 1 plus R3, all the way up to 1 plus Rn, n of them multiplied together. So you can see what the symmetry is. It makes it, in my view, it makes it easier to remember. That compound return is the return if you got, instead of getting different returns every year, let's say you had an investment that the first year returned plus 5%, the second year plus 7%, the third year minus 3%, and so on. At the end of 20 years, you would have a certain amount of money in your account. Instead of getting all those variable returns each year, if you had gotten a constant return, same return every year, what return would you have to get so that you would have ended up with the same amount of money as when you got all those variable returns? That constant return every year, that's the geometric mean return that we're talking about. Now, notice this second bullet point. Let's see if I can find my, here we go. Notice this second bullet point here. The greater the variability of returns over time, the more the arithmetic mean will exceed the geometric mean. If your returns are all exactly the same, every year, 5%, 5%, 5%, 5%, 5%, every year, then the arithmetic mean, if you averaged all those returns, 5%. Geometric mean, if you averaged all those returns, 5%. If they don't change, arithmetic mean and geometric mean exactly the same. If they do change, if you had 5% one year, 4% the next year, 3% the next year, 8% the next year, and so on, if there's some variability, it turns out that the arithmetic mean is always larger than the geometric mean. And the more variability, the more spread out they are, the more that arithmetic mean exceeds the geometric mean. So there you go. Now you know how to calculate another kind of mean. We're going to get to another one in the future here. Here's an example, the geometric mean. An investment account has returns of plus 50% over the first year and minus 50% over the second year. What is the average annual compound rate of return? We also call this, notice, the time-weighted rate of return. I emphasize that because in a little bit we're going to be talking about the money-weighted rate of return, which will be slightly different. Before we calculate the geometric mean, let's calculate the arithmetic mean. That one's pretty easy. We have a return of plus 50%, a return of minus 50%. If you add those two together and divide by 2, plus 50 minus 50 gives you 0%. The average arithmetic return, 0. Plus 50 minus 50, add them together, you get 0. So the arithmetic mean return is 0. But the geometric mean return, remember I told you, if the returns vary, geometric mean is going to be lower than arithmetic. We'll see how much lower. So we take 1 plus the geometric mean return over there on the left side. We have 2 years of returns, so we're going to take the square root of 1 plus the first return, 1 plus 0.5, times 1 plus the second return, 1 minus 0.5. We take the square root of 1.5 times 0.5, that's the square root of 0.75, that's 8.66. That's 1 plus RG is 0.866. Therefore, RG is minus 0.134, or 13.4%. So you lose 13.4% each year. Remember, the arithmetic mean was 0, the geometric mean minus 13.4%. The geometric mean is smaller. If you started off with $100, if you got a 50% return, that'd take you to $150. The second year you lose 50%, now you're down to 75. You started at 100, now you're down to 75. You lost 13% on average the first year and 13% the second year. Not very complicated. These are the questions you have to be able to do quickly on the exam. Remember, on the exam, you're going to have an average of 90 seconds for each question. Some of the questions will take you less time, some will take you more. This should be one, if you practice this, if you get good on your calculator, you know exactly how to do this, this should be much less than a 90-second question. Get good at this, get practice, so on the day of the exam, you're ready to do these quickly. Save the extra time for the icky stuff, the economics and the FRA, where it's going to take you a little bit longer. Do this stuff quickly. Get it right, move on. Okay, another kind of mean is a weighted mean, a weighted average. Instead of having a number of individual data points, and we're going to add all of those data points and divide by the total number, maybe we have data points where we know that a certain percentage of our data points are this, some other percentage is this, and so on. We don't have absolute numbers for those data points, we simply have weights for those data points. A common example would be in our investment portfolio. We have, let's say, stocks and bonds and real estate and some derivative securities. And maybe 40% of our portfolio is stocks, and 30% of our portfolio is bonds, and 20% is real estate, and 10% is some sort of derivative security. We want to come up with an average expected return on our portfolio. We would use the weights, the 40%, the 30%, 20%, 10%. We would use those weights on the individual returns to calculate an average return. So here's the formula. On the left side, notice this is an X bar. Okay, so we know this is a sample, this is not a population. What we calculate is the sum. Here's our Greek letter sigma again. So we have the sum from I equals 1 to n. The weight of each return times that expected return. So this would be the weight that in our portfolio of stocks times the return we expect for stocks. The weight in our portfolio of bonds times the return we expect for bonds. The weight of real estate times the return for real estate. The weight for derivatives times the return for derivatives. That's how you calculate it. Remember, the R's are the individual returns for all the different assets 1 through n that we have in our portfolio, and the weights, remember, have to add up to our entire portfolio. So the sum of the weights down here at the bottom, this is really important, the sum of those weights has to be 1. Now on the exam, they may not give you those weights per se. They may not tell you 40%, 30%, 20%. They may tell you you have $4 million in stock, and $3 million in bonds, and $2 million in real estate, and $1 million in derivatives. You would then have to calculate the weights, which would be the percentage of your total value in each one of those asset classes. So you would take the $4 million plus $3 million plus $2 million plus $1 million, add that together, and you know that your portfolio is $10 million total. And then the weight for stock would be 4 million in stock divided by 10 million total, 40%. So they may not give you the weights directly. You may have to calculate those. Don't let that throw you. That's just an extra small step that you have to put in there. You guys can do this. This is not difficult stuff. You should be able to do this quickly. All right, one more kind of a mean, because you knew we hadn't quite had enough means yet. We got one more for you. This is called the harmonic mean. The way that we commonly use the harmonic mean in finance is to calculate the average cost per share of stock purchased over time. Now notice what it says. I'm going to underline this. In constant dollar, I'm terrible at underlining, in constant dollar amounts here. So this formula will only work if we are buying the same amount of stock each time. We buy $2,000 worth of stock at one price, and then later we buy $2,000 worth of stock at another price, and later $2,000 worth of stock at a third price, and so on. But it has to be the same dollar value for this formula to work. Now, I show you this formula. It says X bar sub harmonic. X bar, that tells you it's a sample. We have this awful looking formula. We have a capital N on the top. Okay, the first problem is previously when we were talking about samples, we were using a lowercase n instead of a capital N. Don't let that bother you. If you would rather see a lowercase n there to make it consistent, just change it to a lowercase n. We take n on the top, we divide by The sum, we're going to add up a bunch of things from 1 to n. We're going to add up n things. But notice we're not adding up the x's. We're adding up the reciprocals of the x's. This formula looks terrible. Let me simplify this. Let me give you 3 steps. Here's step 1. Take reciprocals. You're going to compute the reciprocal of each measurement. So, for example, if you bought $2,000 of stock at a price of $25 a share, you would take the reciprocal of 25, 1 over 25.04. If you bought another $2,000 of stock at $20 a share, you would take the reciprocal of 20.05. And so on. So first thing, take reciprocals of the x values. Values with an S. Take the reciprocals. Okay. Second step, compute the arithmetic mean. So after you have the reciprocals, then you compute the arithmetic mean. The arithmetic mean, of course, you're going to add up all those reciprocals. You're going to divide by n. Third step, take the reciprocal of the answer, of the arithmetic mean. There you go. That's exactly what this formula is telling you to do. You take reciprocals of the x's. Notice we have 1 over x sub I. You would add those all up and divide by n. That's this formula flipped upside down. And finally, you take the reciprocal of that. A little bit longer process than calculating the arithmetic mean, but it's not a difficult process. And if you remember these 3 steps, you will always get it right. Let me give you an example of how this would work in practice. We have an investor who buys $3,000 of stock at the end of month 1 at $20 a share and $3,000 at the end of month 2 at $25 a share. What is the average cost per share for the stock? Now, obviously, one way you could do this is you could figure out how many shares did we buy at $3,000, how many shares did we buy at $20 a share the first time? How many shares did we buy at $25 the second time? Take our total of $6,000, divide by that total number of shares. That would give us the answer. But that doesn't give us a chance to exercise our skill at harmonic means. So we're going to use this as a chance to practice our skills. The first part of this formula here, the leftmost part, is exactly what I just told you. We spent $6,000, 2 times 3,000. The 3,000 over 20, that's the number of shares that we bought in the first month. That would be, let's see, 5 times 30, that would be 150 shares. The 3,000 over 25, that would be 4 times 30, that would be 120 shares. So we had $6,000 divided by 150 plus 120, $3,000 divided by 270 shares should come out to $22.22 per share. Or we can use the formula. Remember, the formula said take the reciprocals. So you take 1 over $20 a share plus 1 over $25 a share. Take the reciprocals, add those up, compute the average, divide that by 2, and take the reciprocal of the answer. So here we go. 1 divided by 20 plus 1 divided by 25. Divide that by 2, take the reciprocal. Either way you look at it, an average of $22.22 per share. Examples for the arithmetic, geometric, and harmonic means. The primary purpose of this example is to show you how these compare. So we have 3 numbers, 2, 3, and 4. Arithmetic mean, we add up 2, 3, 4, we divide by 3, we get 3. Everybody should be able to do that without breathing hard. Geometric mean, multiply 2 times 3 times 4. Notice these aren't returns, so we don't add 1 to any of these. These are just numbers. These are like heights of giraffes. So we multiply the numbers together. We take the cube root. We get 2.88. Notice 2.88 is smaller than 3. Just what I told you before. If the numbers aren't constant, the geometric mean will be less than the arithmetic mean. The harmonic mean, we take the reciprocals of 2 and 3 and 4, add those up, divide by 3, take the reciprocal of that, we get 2.77. Notice that is less than 2.88. When the numbers are not constant, when they differ, the arithmetic mean will always be the biggest, the geometric mean will always be in the middle, the harmonic mean will always be the smallest. That's a good point to remember. If you can't remember that specifically, if they ask you a question about which one is biggest and which one is smallest, if you can do this simple calculation here, you don't even need 2, 3, and 4. Just pick 2 numbers. Use 2 and 3. Make life easy for yourself. If you can do this simple calculation, you will see the arithmetic mean is going to be the biggest, geometric in the middle, harmonic mean smallest. Always works. A simple example will show that to you. All right, here's an example for portfolio returns. We have Dr. Hoover. He has a portfolio with $4 million in cash, $6 million in bonds, and $10 million in equities. So the total value of his portfolio, $4 million plus $6 million plus $10 million, he has $20 million in his portfolio. If returns were 5% for cash, 7% for bonds, and 12% for equities, what was the portfolio return? This is one of those weighted averages about which I was telling you. They didn't give you the weights, but the weights are easy to compute. You add up the total value of the portfolio to get 20 million, so you know the weight on cash is going to be 4 million over 20, or 1/5. The weight on bonds is going to be 6 million over 20 million, that's 30%. Weight on equities, 10 million over 20 million, 50%. So cash, the return is 5%. The weight is 4 out of 20, or 1/5. Multiply the return by the weight, we get 1%. Bonds, a 7% return. Its weight is 6 out of 20, or 30% of the portfolio. Multiply those together. Stocks, return is 12%. Weight is 10 out of 20, or 50% of the portfolio. This is just a weighted average. Weight times return, weight times return, weight times return. Add them up. Weighted average return, 9.10%. Easy to do. Practice this. Make sure on the exam you can do this very quickly. Notice the note at the bottom. The same method works for expected portfolio returns. We're going to see the same calculation when we get to portfolio management. This should make you really happy, because you're going to learn something here in quant, and they could ask you in quant. They could ask you the same thing in portfolio management. You've studied it one time, and you've nailed answers in 2 different study sessions. That should make you feel good. All right, so those are all the different kinds of means. Remember, we're still talking about what we call measures of central tendency, numbers that are somewhere in the middle of our data set. Here's another one. We call this the median. The median, it's the midpoint of a data set. Half of the observations are less than the median, half of the observations are greater than the median. If you have an odd number of observations, 3 of them, 5 of them, 101 of them, 1,000,007 of them, arrange them smallest to largest, pick the one in the middle. If you have an odd number, there will always be one right in the middle. That's your median. So with 5 observations, 2, 5, 7, 11, 14, notice we arrange them smallest to largest. The one in the middle is 7. That's our median. If you have an even number of observations, you have 12 observations, or 102 observations, or 6,842 observations, you won't have one in the middle, but when you arrange them smallest to largest, you'll have 2, one on either side of the middle. Take the arithmetic mean of those 2 and call that the median. So if our data are 3 and 9 and 10 and 20, 9 and 10 are the two that straddle the middle right there. Take the arithmetic mean of those, the average of those, 9.5. Remember when you do this that you have to put the data in order from smallest to largest before you can calculate the median. Don't make the mistake, if they give you a list and they're not in order, of simply grabbing the one in the middle or averaging the two in the middle. Put them in order first. Notice the note on the bottom. This is less affected by extreme values. I want you to highlight that. Put a little check mark by that. Underline it. Put a box around it. Less affected by extreme values than the mean. It's very common, for example, in the U.S. at least, that when they talk about housing prices, that they always talk not about the mean, the average housing price, but they talk about the median housing price. The reason for that is that, take an example. Suppose you had a neighborhood, 50 houses in this neighborhood. Most of the houses are in the $200,000 to $300,000 range, but down at the end of one cul-de-sac, you have some guy who built a $10 million house. Why you would build a $10 million house in a neighborhood of $200,000 to $300,000 houses, I don't know, but people do strange things. If you were to calculate the mean, the average value of homes, that $10 million house at the end of the cul-de-sac is going to raise that mean quite a bit. But it's not going to change the median at all. That's just one number weighed out at the end, and it doesn't matter whether it's 500,000 or a million or 10 million or 100 million. It's out at the end. The median is the two in the middle. So how big that number is at the end doesn't make a difference. That's why when you get data on housing prices, they always talk about the median housing price, because that way extremes at one end or the other don't pull that number at all. That's the common use for median. Okay. Another measure of central tendency is what we call the mode. That's the value that occurs most often in our data set. So here we have data 2, 4, a couple of 5s, a 7, 3 8s, a 10, and a 12. The one that occurs most often is 8. There are 3 of them. That would be the mode. Notice the second bullet point. Data sets can have more than one mode. And if they have 2 modes, we will call it bimodal. If they have 3 modes, trimodal. If they have several modes, we might say multimodal. Now, I'll tell you something about statisticians. Statisticians are a strange kind of mathematician. Mathematicians tend, I'm a mathematician, so I can talk about mathematicians. Mathematicians tend to be very precise, very exact with their language. And if we as mathematicians said that mode means the most frequently occurring data point, the one that occurs most frequently, and we had 3 8s, then the only way we could have more than one mode is if we had 3 of another number. If we had 3 8s and, like our data set here, 3 8s and 2 5s, well, 2 5s is not as many as 3 8s. A mathematician would not say that this is multimodal. They would say it's got one mode and that's 8. Statisticians are a little bit sloppier than that. And if a statistician saw a distribution that looked like this, then a statistician would say that this is a mode, and he would also say that this is a mode. Oh, I can't put those 2 dots together. Okay, I'm going to have to find something else other than those dots. Anyway, the statistician would say that this is bimodal, this is a mode, and this is a mode. A real mathematician would not say that. They would say, no, this is the one that's most frequent, that's not nearly as frequent, that's not a mode. Statisticians say, well, in its own little neighborhood, for numbers really close in here, this is the one that occurs most frequently. And for this one over here, in its own little neighborhood, this is the one that occurs most frequency. So statisticians, they have this nice definition of a mode, and then they tend to abuse it by calling something like this bimodal. Just something to bear in mind. That's the way statisticians talk. I don't agree with it, but that's the way they talk. You should be aware of it. It could come up on the exam. All right, another way of describing data is what we call quantiles. We're going to divide the data up into a number of groups. All the groups are going to be the same size. The most common numbers of groups that we have would be 4. We call those quartiles. So 0 to 25% of the data, 25 to 50% of the data, 50 to 75, 75 to 100. Quartiles. Quintiles, divided up into 5 groups, 0 to 20, 20 to 40, 40 to 60, 60 to 80, 80 to 100. Those would be quintiles. Deciles, the second one there, chop it up into 10 groups. And percentiles, drop it up into 100 groups. Divide it up into 100 groups. Once you have it divided up into the groups, then we would say, for example, that 75% of the data points are less than the third quartile. The first quartile is at 25, second at 50, third at 75. 60% of the data points are less than the sixth decile. The first decile is at 10%, the second one's at 20, and so on. The sixth is at 60, the seventh is at 70, and so on. Okay? What you really need to know is this bullet point, this sentence right down here. And that is that if you have a certain number of observations, 17 in this example, the 70th percentile, to calculate which observation will be at the 70th percentile, you take the number of observations and you first add 1. Why do you add 1? Well, the technical reason for adding 1 is that you take your smallest observation and put it down at 0, and your largest observation and put it up at 1. So you have one more observation than you have intervals. Think of it this way. Let's say you had 3 data points. You had 1 at 0, 1 at 50%, 1 at 100%. The 50 percentile would be at your second data point. That's 50% times 4, times 3 plus 1. So just remember that to figure out which data point falls at a particular percentile, take the number of observations, add 1, multiply by the percentile. That tells you which data point falls at that percentile. So if we have 17 observations, the 70th percentile falls at data point 12.6. And you're thinking, wait a minute, I have data point 1, I have data point 2, I have data point 12, I have data point 13. I don't have a data point 12.6. Well, we say that it's 6/10 of the way between data point number 12 and data point number 13. So if it doesn't come out to be a whole number, then it's part of the way between, in this case, 12 and 13. So make sure that you can calculate which data point falls at a particular percentile. Remember, let me put a box around it. Remember to add 1 to the number of your observations. I will guarantee you on the CFA exam, if they ask you this question, one of the wrong answers will be the answer you would get if you forgot to add that 1. CFA Institute knows the kinds of mistakes people make. They will always give you wrong answers that exploit the common mistakes that you make. You guys aren't going to make that mistake. You let somebody else make that mistake. Okay, moving on to the next. Oh, then I'm sorry. We had my mistake. We had this cute little arrow pointing down to the 6/10. Okay, cool. All right. Enough about central tendency. Now we want to get an idea of how spread out our data are. 2 ideas for how spread out our data are. One's called the range, one's called the MAD, mean absolute deviation. We have four numbers. Annual returns for a particular stock. 15% the first year, negative 5% the second year, 12%, then 22%. The range is simply the difference between the largest and the smallest. Our largest return over these 4 years was 22%. Our smallest return was negative 5%. The difference between 22 and negative 5 is 27%. Remember, when you subtract a negative number, it's adding a positive number. Don't take 22% minus negative 5 and get 17. That will be one of the wrong answers CFA Institute will give you. Be careful. Now, the mean absolute deviation. This takes each of our data points, our 15, our negative 5, our 12, and 22. It figures out how far that is away from the mean. So first we have to calculate the mean. All right, we come over here and calculate the mean. Add those four up, divide by 4, we get 11%. Now, just as an aside, if all we did was if we took 15 minus 11, and if we took negative 5 minus 11, and if we took 12 minus 11 and we took 22 minus 11, and we added all those up, forget about these absolute values for a second. If we just took 15 minus 11 plus negative 5 minus 11 and so on, if we added those up, we would always get 0. It always works that way, because some of our numbers will be positive and some of our numbers will be negative. That won't tell us anything about how spread out they are when you always get an answer of 0. So one way to figure out how spread out they are is get rid of the negative signs on those negative numbers. 15 minus 11 is 4. That one's okay. Don't need to do anything about it. Negative 5 minus 11. Ooh, that's negative 16. Get rid of that negative sign. That's where the absolute value comes in. 12 minus 11 is 1. That one's okay. 22 minus 11 is 11. That's okay. If you take absolute values here, you get rid of the negative signs, then you get a mean absolute deviation of 8%. That's a measure of how spread out the data are. The bigger the MAD, the more spread out your data. The smaller the MAD, the less spread out your data. This is a perfectly good measure of how spread out the data are, and yet it's one that statisticians don't tend to use very much. And I'll explain to you why, because when I explain to you why, it will help you better remember the mean absolute deviation. If you remember from your high school algebra, the graph of the absolute value function, those are my axes. I know, they're terrible looking axes. They're not straight. Well, that's just how good I am at drawing with a mouse. Let's see if I can come right down here to this point. There we go. That's the graph of the absolute value function. It's supposed to have a sharp point right down here at the bottom. Slope of negative 1 coming down here, slope of positive 1 going up there. The reason that statisticians don't like using this absolute value function is we have a sharp point right there. And what's wrong with a sharp point? In a word, calculus. You cannot do calculus when you have a sharp point, and statisticians are gaga about calculus. They love doing calculus. If you can't do calculus, they hate it. So that's why they don't use mean absolute deviation. If they want to get rid of the negative signs, they're going to do something other than absolute value, so they get a nice smooth curve here and they can do calculus, and then they're just happy as can be. How do we do that? We look at the next slide. Variance and standard deviation. One way, go back to the previous slide, one way that we can get rid of those negative signs in how spread out the data are, we can take absolute values. Another way that you can get rid of the negative signs is to take those differences, our data point minus the mean, and square it. You know that if you take a negative number times a negative number, it's positive. If you square a negative number, you get positive. If you square a positive number, you get positive. One way to get rid of the negative signs, square everything. What's the advantage to squaring everything? I'll draw you another cool picture. You're going to forgive my axes here for a second. Here's my vertical axis. Here's my horizontal axis. If you square What's the graph of a square look like? It's a parabola. It's nice and smooth. No sharp point down here. You can do calculus. Statisticians love to do calculus. That's why they squared this thing. So you take each observation. Let's go back to our giraffes. We take the height of each giraffe. Giraffe 1, giraffe 2, giraffe 3, all the way up to giraffe 50,842, or whatever, however many giraffes there are in the world. Subtract the mean. Notice this is a mu. What does that tell you? We're working with a population here. Take the height of each giraffe minus the mean, square it. Make sure we get a positive number. Add those all up. That's our sigma here. Add up all those squares. Divide by n. Divide by the total number of giraffes. That gives us something that we call sigma squared. This is a lowercase Greek letter sigma. Greek. Tells you we're working with a population. One of the problems with working with variance is the units that you have. Remember, we were measuring the heights of giraffes in meters. So this is in meters, this x sub I is in meters, mu is also in meters. We have meters minus meters, that gives us meters. When we square it, that gives us meters squared as the units on variance. Now, meters squared probably isn't such a bad unit. Most of the people watching this video will probably be able to visualize a meter squared, a square meter. Look down on your floor at your carpeting. You can figure out a meter by a meter squared. That's not too bad. You can visualize that. But suppose instead that our data, instead of being the height of the giraffes, suppose we had pricing data for a bunch of stocks, and it was all measured in dollars. Then this x would be in dollars, and that mu would be in dollars, and the difference would be in dollars, and when we squared it, we would get dollars squared. I don't know about you, I look in my wallet, all of my dollars are rectangular, they're not square. Trying to visualize a square dollar, that's a kind of a strange unit. So, because the units here are the square of the units we started with, not too many people like that. They like to go back to the original units. That's where standard deviation comes in. Standard deviation over here, sigma, standard deviation of a population. We take the square root of sigma squared. We take the square root of the variance. What's the advantage here? It's in the same units as your original measurements. If you're measuring heights of giraffes in meters, standard deviation will be in meters. If you're measuring the value of stocks of a particular company in dollars, standard deviation will be in dollars. If you're measuring percent returns on an investment, standard deviation will be in percent. Always the same unit as your underlying data. Makes it very easy to understand. So here we go. Variance, standard deviation for a population, easy to compute. You can actually do this fairly easily on your calculator as well. Now comes the tricky one. Sample variance and sample standard deviation. Sample variance is called S squared. Sample standard deviation is called S. Of course, it's a sample, so we don't use Greek letters, we use English letters. Here's the key. I want you to put a box around this denominator. Notice the difference. For a sample, we do not divide by n. For a sample, we divide by n minus 1. Do me a favor. The mathematicians have a good way of remembering this, and I think it's a good idea. So I want you to put this in. Up here on the top where it says sample variance and sample standard deviation, I want you to write in two words, hyphenated, right here. Bias hyphen adjusted. Write that, so it's the bias adjusted sample variance and the bias adjusted sample standard deviation. This is actually the proper term in mathematics. What we mean by that, and I'm not going to go into the technical details on this, have to do with degrees of freedom and a bunch of things you don't really want to know about. But the basic idea is that if we divided by n here, instead of dividing by n minus 1, we would have the situation where the average value of our sample variance would not be the same as our population variance. The average value of our sample standard deviation would not be our population deviation. And remember, the only reason that we calculate all these statistics on our samples is that we're trying to infer some statistics on the population. Why do we calculate a sample mean? Because we think it'll tell us something about the population mean. Why do we calculate a sample standard deviation? Because we think it'll be useful in telling us something about the population standard deviation. If we divided by n, then these numbers would not tend to converge to the value for the population. They would be off by a little bit. When we divide by n minus 1, they do converge to the value for the population, and that's what we want. And that subtracting 1, that adjusts for the bias in this statistic. So if you throw that word bias adjusted up there, actually it's two words hyphenated, bias adjusted, you throw that in there, that will help you remember for a sample, standard deviation, sample variance, divide by n minus 1. Make that little adjustment, and then you'll get it right. Remember, CFA Institute, when they ask you this question on the exam, one of the wrong answers is going to have divide by n. You guys are going to get it right because you're going to remember to divide by n minus 1. Let somebody else divide by n and get the wrong answer. That's not something you need to worry about. You're going to get it right here. All right, let's do some examples. Returns on 4 stocks are 15%, minus 5%, 12%, and 22%. What are the population and sample standard deviation? The population mean is 11%. We already calculated that. How do we do the standard deviation? We take 15 minus 11, minus 5 minus 11, 12 minus 11, 22 minus 11. And I want you to notice something here. Notice they got rid of all the percent signs. This is very common in finance. They really should have 15% minus 11%. Finance people never do this. So these numbers, it's not really 15, it's really 15%, but this is the way finance people talk. We divide that by 4, we get 98.5. Again, it really should be 98.5, and the units should be percent squared. Remember, percent means divide by 100, so it really should be divide by 100, divide by 100. This number, 98.5, it's too big by a factor of 10,000, but this is the way finance people talk. This is the way CFA Institute does it. This is the way you have to be able to do it on the exam. Take the square root of 98.5 and you get 9.9. Now they remember to throw in the percent sign. For the sample standard deviation, numerator is the same. 15 minus 11 squared, minus 5 minus 11 squared. But now what's the difference? The denominator. We don't divide by 4, we adjust for the bias. We divide by 3. We get 131, square root of that, 11.5. Again, that 131 properly, too big by a factor of 10,000. This is the way they do it. How do you do this now on your calculator? I'm going to show you on the TI BA2 Plus calculator how you do this very, very easily. I have some notes that I wrote down here about this. We'll get to that. So you turn on your TI calculator. First thing you do is you hit the second button, which is up there in the upper left, and then the number 7. Second, number 7, that puts you in data mode. Right above the 7, you'll see data, so you're in the data mode. Next, hit 7 and the clear entry clear button. If you had any numbers at all in the memory in data mode, this clears them out. Really, really important. Make sure when you're doing this calculation, when you're doing time value of money calculations, any of that, make sure you clear out your calculator. Take that extra half a second to hit those 2 buttons and make sure you don't have stray data, because otherwise you're going to get an answer that makes no sense whatsoever. It's going to frustrate you. You're going to scream, which the proctors on the exam aren't going to like at all. Just clear out your calculator. All right, so our calculator is now cleared. We want to put in our 4 data points, our 15%, our minus 5%, our 12%, and our 22%. Your calculator is looking for x's and y's. We're only going to be giving it x's in this case. So we put in 15, press enter, hit the down arrow, and then hit the down arrow a second time. When we hit the down arrow the first time, it says, oh, now I want your y's. We're not giving it y's, we're only giving it x's. So hit the down arrow a second time, say, nah, we're only talking about x's now. Now we're ready for the second x. Put in a minus 5. Remember that to do that, you put a 5 and then the plus minus sign to change it. Minus 5, enter, down arrow, it'll ask you for the y, down arrow. You tell it we're not doing y's, we're just doing x's. Move on to the next slide. Put in your data point 12, put in your data point 22. Again, 12, enter, down arrow, 22, enter, down arrow. Now we have all the data in. We have our 4 data points. Hit that second button, that gray button up there in the upper left, and the 8. That enters statistics mode. Right above the 8 on your calculator, you'll see stat. We're going into statistics mode. And then hit second and enter. Now when you hit enter on the display, you may get 1 minus v. That would be ideal. That's what we're looking for, 1 variable statistics. But when you do it, depending on what you were doing on your calculator earlier, it might say ln or it might say exp. Just keep doing that, keep scrolling through until you get to the 1 minus v. That tells you you're in statistics mode for 1 variable, and now you can start looking at the statistics. If you scroll through, once you get to the 1 minus v, you hit that down arrow, it will scroll through all of the statistics that you have. And the statistics that it will show you, first it will show you n, the number of data points that you have. Then it will show you the average. It shows it as x bar, the average that you have. Next it will show you S sub x, the sample standard deviation. Next it will show you sigma sub x, which is the population standard deviation. So the calculator doesn't know whether you're treating these data as a population or a sample, so it doesn't know whether to divide by n or n minus 1, so it gives you both. It says here first is the sample standard deviation, next population standard deviation. It also shows you the sum of all of the x's, so it shows you a sigma x, and it also shows you the sum of all the squares of the x's, sigma x squared. So as you push this last down arrow, that's this one right here. As you scroll through it doing this, it'll scroll through n and x bar and s sub x and sigma sub x and the sum of the x's and the sum of the x squareds. And if you hit it again, it'll go back to n. It'll scroll through them again. So very easy. You put in all the data. Your calculator does most of the work for you. You just need to scroll through and find the one, whichever one they need on the exam, that's the one you can find. All right, on to some more exciting stuff. Chebyshev's inequality. Chebyshev was a Russian mathematician. The way that we've written Chebyshev here, Chebyshev, that's only one of about 1,700 ways that you can write Chebyshev using English letters. He was a Russian mathematician who did a lot of work with statistics. One of the things that he discovered, which we call Chebyshev's inequality, really interesting result for mathematics. It says that if you have any probability distribution at all, this is really important because most of the rest of your quant is going to be talking specifically about normal distributions. Chebyshev's inequality says, I don't care whether it's normal or not. It could be normal, it could be binomial, it could be uniform, it could be Poisson, it could be some strange, weird, nobody's ever given a name to it probability distribution. Any probability distribution at all, Chebyshev's inequality says that if you start with the mean in the middle, so let me draw a picture here. Okay, we got our line. By the way, I want you guys to be really good at drawing pictures. When you're working this stuff out on the exam, you should be able to draw pictures. When you're doing time value of money, you should be able to draw timelines. When you're doing problems with Chebyshev's inequality, you should be able to draw normal distributions and means, draw a mean and draw a sigma. So right here, that's going to be our mean. There's our mean. Over here, that's plus 1 sigma. That's supposed to be a sigma. Down here, that's minus 1 sigma. Okay, so that's our mean plus 1 sigma, our mean minus 1 sigma. We could go down 2 sigmas, 3 sigmas, 5 sigmas, 10 sigmas. What Chebyshev's inequality says is that between these two numbers, k sigmas, up and down, 1 sigma up and 1 sigma down, 2 sigma up and 2 sigma downs, there will always be at least this fraction of our observations in this range. So if we're talking about plus or minus 1 sigma, okay, that one's not very interesting, because if k is 1 for 1 sigma, well, you get 1 over 1, which is 1, and 1 minus 1 is 0. So at least 0 of our observations are between there. Okay, that's not an interesting one. Let's say we went plus or minus 2 sigma. Let me throw a 2 in here. Plus or minus 2 sigma. That's a 2. So our k is 2. K squared is 4. 1 over k squared is 1/4. 1 minus 1/4 is 3/4, or 75%. That says that between mu minus 2 sigma and mu plus 2 sigma, at least 75% of the observations have to lie in that range. And it doesn't matter what the distribution is, any probability distribution, this is true. Suppose we were at 3 sigma. 3 squared is 9. That's 1/9. 1 minus 1/9 is 8/9. At least 8/9, 0.888. 8/9 of our observations have to be between mu minus 1 sigma and mu minus 3 sigma and mu plus 3 sigma, and so on. That's Chebyshev's inequality. They could easily ask you a question about that. Works for any probability distribution. Really cool result. All right, a few more calculations here for you. One is called the coefficient of variation. It's a measure of risk per unit of return. We take our standard deviation in the numerator, divide by our mean in the denominator. So come over here, draw a little box, put it around. Here's the formula that you want. Standard deviation on the top, mean on the bottom. That's the coefficient of variation. So for example, for asset A, we have a mean of 5%. These are our measures of return. So mean return is 5%, standard deviation of returns is 10%. For asset B, average return 8%, standard deviation of returns 12%. We calculate the coefficient of variation for A. 10% over 5% gives us 2. Coefficient of variation for B, 12% over 8% is 1.5. Because we have the risk number on top, we would obviously prefer lower risk, so the smaller the coefficient of variation, the better. If you're comparing two investments, the smaller the coefficient of variation, the better. That's CV. Got to be able to do that calculation. Easy calculation, you just have to remember what goes where. Remember, it's standard deviation on top, mean return on the bottom. Okay, now we're going to take that CV and we're sort of going to flip it on its head and come up with the Sharpe ratio. Very, very important. CFA Institute loves Sharpe ratio. Sharpe ratio is going to show up here. It's going to show up in your portfolio management. It's going to show up at level 2. It's going to show up at level 3. You are going to be Sharpe ratioed to death by the time you earn your CFA charter. This thing, as I said, flips the coefficient of variation on its head. Now we put return on the top and standard deviation of returns on the bottom. First thing you have to do, box this off, make sure you got this, know the definition of the Sharpe ratio. Okay, we have in the numerator, we have R sub P bar. That's the expected return on the portfolio. We're talking about the Sharpe ratio for a particular portfolio. So this is the expected return on the portfolio minus RF bar. That's the expected risk-free interest rate. I don't know why they abbreviate risk-free interest rate as R sub F. The R is the rate. YF, it should be RF for risk-free, but this is the way they do it. Don't ask me why. They didn't ask me. If they'd asked me, I would have told them it was stupid. But this is what they do. R sub F bar. We take the expected portfolio return minus the expected risk-free rate, divide it by sigma sub P, the standard deviation of the portfolio's returns. So notice, on CV, we had risk in the numerator, average in the denominator. We had standard deviation in the numerator, average return in the denominator. Sharpe ratio, we flip that over. We have the average in the numerator, we have the standard deviation in the denominator. The way to think about the Sharpe ratio, this the return on the portfolio minus the risk-free rate, that's the expected excess return. How much extra return are we getting for not investing in a risk-free asset, for investing in a risky asset? In the denominator, we have how much risk do we have to take on to get that extra return. Obviously, we would like to have a lot more extra return and not a lot more risk. So we'd much prefer having a big number in the numerator and a small number in the denominator, so we would like a high Sharpe ratio. Higher is better for Sharpe ratio. Another way to think about this, if you look at this red box in the bottom, think about Roy's safety first criterion. Safety first, instead of using the risk-free rate, instead of subtracting the risk-free rate, we subtract a target rate, a minimum required rate. We take the return on our portfolio minus the minimum required rate over the standard deviation of returns. That's Roy's safety first. The Sharpe ratio is just Roy's, where we're saying that our minimum required return is the risk-free rate. Gotta know how to do this calculation. Again, not difficult, but you have to be able to do it because it's going to show up on your exam. Okay, we're winding down here now. We only got a few more slides to go. Bear with me, hang on, we're about to get done with this. Okay, the next idea, skewness. Instead of having a symmetric distribution, the same on the right side of the mean as on the left side of the mean, maybe we have a distribution that has a lot more observations on one side than the other. That would be measured by skewness. It measures how much lack of symmetry. Do we have a lot more on the right than on the left? Do we have a lot more on the left than on the right? Skewness measures that. In your textbook, in your study guide, they give you a formula for calculating skewness. The LOS does not say you have to be able to calculate it, it says you have to be able to describe it. I definitely would not spend a lot of time trying to memorize that formula for calculating skewness. They're going to tell you the skewness, or more likely, they're just going to ask you general questions about skewness. So, first understand symmetry. If we have a symmetric distribution, the skewness is equal to 0. If we have one like this picture, the picture that we have here is supposed to depict a normal distribution. Notice the mean, right down the center, is the same as the median. 50% on the left, 50% on the right. It's the same as the mode. That's the biggest point, right there in the middle. When it's symmetric, when you have a normal distribution, the mean is equal to the median is equal to the mode. On the next slide, we're going to show you this is a distribution with positive skew. It is skewed to the right. Longer tail on the right, shorter tail on the left. Go down here to the bottom. This is an easy one to remember. I want you to remember this, and I want you to remember what's on the next slide. And the way to remember what I just boxed off is take those three words, mean and median and mode, write them alphabetically. Mean first, median second, mode third. You have to write them alphabetically. If it's skewed to the right, between each pair of words, draw a little arrow pointing to the right. On the next slide, when we talk about negative skew, we're going to draw little arrows pointing to the left. This always works. It's a really easy way to remember it. If we're skewed to the right, our arrows are pointing to the right, the mean is going to be bigger than the median is going to be bigger than the mode. Very easy. Skew, if you have absolute values, notice up here, absolute values greater than about 0.5 are significant. If they're less than 0.5, they don't really matter much. Don't worry about them. Okay, remember, the mean is the one that's affected by the outliers. That $10 million house at the end of the cul-de-sac in the neighborhood that has $200,000 to $300,000 houses. That really pulls the mean over, doesn't affect the median at all, doesn't affect the mode at all. We move to the next slide, and remember what I said just as on the previous slide, box this off. Write down the words mean, median, and mode alphabetically, left to right. If it's skewed to the left, draw little arrows pointing to the left. The mean is less than the median is less than the mode. Very, very easy to remember. Good mnemonic device. You'll never forget it. You will nail these questions on the exam. All right, next we come to kurtosis. Kurtosis, this gives you an idea of whether or not your probability distribution has a higher peak in the center than a normal distribution. We'll talk a lot about normal distributions in the next study sessions, but for right now, just understand that a normal distribution has a kurtosis of 3. And usually we don't just talk about kurtosis. We usually talk about what we refer to as excess kurtosis. So do you have a distribution that has kurtosis more than 3, positive excess kurtosis, or less than 3, negative excess kurtosis? It measures whether or not you have a higher peak in the middle or whether or not it's somewhat flatter in the middle. The term for a higher peak where you have positive excess kurtosis, put a box around this, is leptokurtic. If we had, I'll try to draw this in, I'm not going to do a very good job drawing it, but if we had one that was flatter than that normal distribution, that's supposed to reflect a flatter distribution. I kind of messed it up, but you get the idea. Okay? The term for this, write this down, platykurtic. That's this flatter one down here. I used to work with this engineer years ago, and he remembered platykurtic and leptokurtic by thinking of Australia. Platykurtic, think of a platypus, you know, a little flat mammal, has a duckbill, sharp claws, flat, squashed down flat. That'll remind you of platykurtic, it's flat. For leptokurtic, he thought about kangaroos. Kangaroos leaping about. Yesterday a kangaroo leapt over a fence, jumped really high. Leptokurtic, jumps high. That will help you remember leptokurtic, has a high center. Platykurtic is flat. If you really wanted to know if you have kurtosis equal to 3, if you have your normal distribution, the name on that one is mesokurtic. It's not going to show up on the exam, just kind of fills out the information. Know what it means to be leptokurtic, platykurtic. Leptokurtic, you have positive excess kurtosis. Platykurtic, negative excess kurtosis. Obviously, for a normal distribution, because its kurtosis is 3, it has 0 excess kurtosis. You generally only need to worry about excess kurtosis when the number is greater than 1. Okay? So if you have a distribution that has kurtosis of, say, 2.4, well, then your excess kurtosis is minus 0.6, probably not significant. You have another distribution that has kurtosis of 3.3, your excess kurtosis is 0.3, probably not a big deal. But if you had kurtosis of less than 2, I don't know if you can have kurtosis of less than 2. I don't think you can. But if you had kurtosis of, let's say, 4, that would be significant. All right, some examples on investment returns. Consider a sample of investment returns over 5 years. We got 10% the first year, 15% the second year, negative 4%, 9%, 5%. Arithmetic mean of 7%. We added all those up. We divided by 5. We got 7%. What is that 7% going to tell us? That says that next year, we are most likely, our best estimate of what the return is going to be next year, 7%. It's a 1-year estimate. Take the arithmetic mean, that's the best estimate of what we'll get next year. The geometric mean, 6.81%. Remember how you calculated that. You took 1 plus 10%, 1 plus 15, 1 plus negative 4, 1 plus 9%, 1 plus 5%. You multiplied all those together. You took the fifth root. You subtracted 1. That's where you got 6.81%. That's the best estimate of your compound return over future years. So we have our 5-year compound return for these 5 years. If we went to the future, had 5 more years, the best estimate of the compound return over that period of time, 6.81%. If we only want to look at 1 year, arithmetic, 7%. And that, my friends, is the end of this reading. I hope you enjoyed it. Come on back. We got more quant for you in the next reading.